Good morning. All right, can you guys hear me? And get feedback. Okay, great. Okay, so lecture notes today are on the handouts and lectures. If you do have your computer and want to download those for today, apologize again. It's late last night again that they got put up. So today I also was able to start getting more materials. So you should have access now to the Laplace transform method. So this is our unit. So there is starting to be some material there. So under the learning materials, you're going to find some math background for the Laplace transform. So, these are great videos on explaining what I went through pretty quickly. So if you want a little bit more time with them, feel free to go back and go through each of these videos, which is great about the Laplace transform, the properties. We're going to look at, this is all like the math background. And so we're going to look at applying all of them. So whatever you feel like you need, to get to the level of, I can understand this enough to apply this is where you want to be. Then this is what we're going to go over today is the partial fraction expansion. So there's not a lot of material here yet, but I will again give you some additional material with some testing your knowledge. And then the end goal is to be able to solve what we had been working on before in the S domain to solve similar circuits that we've already seen. But now you have input sources that can be more than just a constant or just a sinusoid. It can be a complex input with multiple ups and downs or ramps or whatever signal. Plus we can do now the method of more than just two components of an L or a C. We can do LLC, we can do fifth order, meaning 5 of those elements in a circuit using these techniques. So that's where we are. Any questions so far? Yes.
So when we were dealing with the S domain, I was just curious, like what exactly the major difference domain and because like I understand that like we're dealing with the function as a function. But as we go to the S domain, we're dealing with frequency domain. What are the differences? Like,
so the biggest advantage of going to the S domain, so you can think of the S domain as like an imaginary domain. It's not a real physical domain like time is. What it allows us to do, yes, do you want to?
is it kind of like the substitution?
It's a little different than U substitutions still. It is like an imaginary system of things that, let me think of how to explain it better. Yeah, that's a good way to look at it. You guys have looked at like polar transformations. So you move from the time domain into like polar coordinates. So you have an imaginary and real. Draw this on here. So instead of time versus some variable, what we have is very similar to the real axis and the imaginary axis. Can't type, but imaginary. Just put I. I should put little I. Okay, I'll put J. So imaginary and real axes, that is very similar. And what we're going to actually see is that if we don't get it to in this class, is what you're going to see is that S can be relatable to J omega. And then it helps us understand frequency. And so, yes, complex plane is a great way to think about this. Think about the S domain as like, okay, this is my complex domain. Does that help?
Still a little confused about the main difference between the complex domain and the frequency domain. Is it just like that relationship S equals JW?
Yep, it's just S is the same as frequency. It's just the J is in there. So it's just on the imaginary axis, the value of your magnitude there.
All right, thank you.
Hopefully that helps. Okay. So yes, think about the S domain as a complex domain. And that hopefully can help you be like, okay, I'm moving to just another domain. And in this, the biggest advantage is now our integration and differentiation is an addition or subtraction, which is way easier to work with. And so to be able to do that, we're going to go over what sometimes when our equations get to a point like this, it's going to be a little bit hard to match them up to the tables. And so what we need is a few more techniques in math to be able to like manipulate those equations to match them up with the table. So that's our end goal is that we want to match them up with already existing Laplace transforms so we don't have to do all of that integration. And so we can just use a table and match them up. But sometimes the equations don't look exactly like that. So we're going to look at that a little bit later today. Going back though to this, which was where we ended last time. So we ended how did we do this last time? Anybody want to take a stab at summarizing this? What were our steps to solve the circuit? Okay, first step. Correct. So transform into S domain. What did we do after we transformed it into the S domain? Correct. So using just our normal techniques, created the set of equations that we need. Can type equations. Okay. Then what? Okay, good. Solve for unknowns. So I'm going to just put with the S variable. So now everything is in that S domain. So then our solution is with S in it as the variable. So then we needed to do one more step in order before we can transfer back. Correct. So we have to manipulate the equation to get it into the form to match up into the table. So you manipulate the solution. So manipulate the solution to match the forms on the Laplace tables. From there, last step would be inverse Laplace. Okay, so these are basically our steps. So we first changed it into the S domain. So we changed the input source to I of S. And then we changed R goes right to R, L goes to L, or to SL, and then either this form or, oh, I don't have the rest of them, or you can do it in the voltage form, which is the inductor with the voltage source in series. So depending on whichever one is going to be more convenient for you to analyze the circuit with, that would be the form you would pick. Yes.
If you ever choose one where you have one that's in like a parallel form and one that's in a series form.
Yeah, so if just again, depending on your circuit, you don't have to have both of them be in the series form or both of them be in the parallel. If it makes it easier to translate for some reason, you could pick one in a parallel form and one in a series form. So it doesn't, it's just unique to each element in there. It doesn't matter which one you pick. Both are going to yield the same solution. So it's just a matter of how many equations do you need to solve for that unknown variable. So in this case, it was easier with our initial conditions were 0. But if we have a case where they're not, you would put a value in for the current source in this case. Then we did node voltage. So we had minus IS plus Vx over R plus Vx over SL plus SC Vx, which was Vx over 1 over SC. And then we solved for Vx, and then we saw that IC was V, or you can say that Vx was IR, and the R in this case is 1 over SC. So then that means IC is Vx times SC. So that was where that came from. And then now we plugged in the equation for Vx here. And now we're going to get it into the form where we have just a single S, because that was where the tables we see here on these tables that we either need to get it into one of these forms if we have an S squared, or we need to, but none of them have a variable in front of it. So we want to move out that variable so that we can try and match them this way. The other form that we can, oh, sorry, there's this one too, is the factorization if they do factor out equally, or if they're able to factor into two multiplications like this, let's see, like this one, we can use this partial fraction expansion. And so we're going to go over the partial fraction expansion. So those are the forms we're trying to get to match them up with the table. So the goal on this manipulation now is to get that S squared by itself to see, does that match up right there? If not, we need to look and see, can we or is it factoring when you get it into this form?
Yeah.
Is that what you guys call it? Okay. If you want to factor it so you can get it into this form, then we can do the partial fraction expansion, which puts it in some unknown variable over each of the portions of this. And so we know 1 over S, and then if we have a constant A, then it's just A. S plus 2. Here's, 1 over S translates into just a 1 U of t. 1 over S plus A translates into e to the minus AT U of t. So each of those has a match on this table. So that is our goal, is to then manipulate this equation. So all right, so then I brought out this C because I saw that the C here is a constant, so I can bring it out and still get the same equation there. And then from here, I added in the I of S. So from here, I'm going to now multiply these together. And so I have S squared over S gives me 6. And one of those S's is going to be removed. And then it's a minus, again, 6, or S squared divided by S just gives me 1S. So from here now, I need to try to factor that denominator, right? Bottom's denominator. All right. Lost my book. Sorry, lost my book. Okay. So if you remember back to quadratic formula, to be able to solve for this, the quadratic formula is, this is equal to 0. We have x is equal to minus b plus or minus the square root of b squared minus 4ac over 2a. So we can use this to solve for that quadratic if we don't just see what the factorization is. And so that gives us minus b will be a minus 1 over RC plus or minus the square root 1 over RC squared minus 4 times 1 times LC and then over 2. Okay. So this makes it hard without having the values. So if R is 125, L is 0.1, and C is 4 milli, we can just look at kind of each of these as an addition, so we can solve each one and then just add them together. Yes.
Shouldn't the numerator have S squared, not S? Because you- Oh, I see.
Yeah, S squared divided by that S.
Yeah, sorry. I didn't see that.
No worries. Is that, so there still is an S in the top?
Yeah.
Yep, just one because of that s squared divided by that s. And then in the second one, it's divided by that s. So now we have, two kind of components and we can look at them separately and then solve for that. So looking at IC1, which is 6s. And then this becomes s squared plus 2s plus 2,500. And we get S1, sorry, factor it this way. S plus 1 plus 50J, S plus 1 minus 50J. So putting this into that quadratic gives me a -2 plus or minus the square root 4 minus 4 times 2,500 all over 2. So that becomes a -1 plus or minus the square root of approximately 2499. And so that's where the -1 plus and minus the 50J come from. So now that I have this, I'm going to do a partial fraction expansion to solve this. So what that means is I have some unknown variable, A over S plus 1 plus 50J plus B over S plus 1 plus 50J. Sorry, minus. Plus 1 minus 50J. All right, and you find these by multiplying the original equation by whatever's on the bottom. So A, you're going to say it's S plus 1 plus 50J times the 6S all over S plus 1 plus 50J minus 50J. And then these cancel. And I'm going to evaluate this at S when S is a -1 minus 50J. So now when I put those in, I get 6 times -1 minus 50J all over S plus 1 minus 50J. Oh, sorry. Put that in. Okay. And then, let's see, -1 minus 50J plus 1 minus 50J. Okay, so then this becomes a -6 minus 300J. And then the ones cancel and I have a -100J. So if you remember, a minus, like a 1 over J can also become a minus J. So I can bring that one up. And a -1 over J will become a plus J. So this will become a -6 over 100J. Minus 300 over 100. They both pluses. No, plus, minus. Come. Maybe. Okay, somebody want to put this on a calculator? My calculator's not coming up. So this is where I turn to a calculator because I sometimes make mistakes with the signs. But if you're in, so we want to get this and then change it over to polar from this rectangular form. Still thinking. Hopefully. Sign in. Yes, frustrating. Here we go. Okay. Okay, so -6 minus 300 J over minus 100 J. Needs to be, oops. Yep. No. So 3 over the square root of 2505 or 1 is approximately 3. And then the inverse tangent of 1 over 50 ends up being the minus 1.15 degrees. So use a calculator. Or you can do it by hand if you want, but that would be, you want to get it into the polar form. And now the B is going to be the conjugate of this. So now our IC1 is going to be 3e to the minus j 1.15 degrees over s plus 1 plus 50j plus 3e to the plus j 1.15 all over s plus 1 minus 50j. So the nice thing about the complex is once you find one, it's going to be just the conjugate of the other. And remember, the conjugate just means that instead of a minus, you'll put a plus where the j is for this one. So now we can look at the table. and look for an S, a match there, which we had an S plus 1 plus 50J. And then we have the opposite. So it looks like it's going to be this form. So we can go back up and, double check, does this look the same? And we have e to the j theta plus e to the minus j theta over an s plus a plus jb. So now we need to identify what is each one. So what's the differences here?
Your positive j term, like you have should be. I mean, doesn't j theta.
So we can swap those two so they're exactly in the same location. So we can put the positive first. What about the 3? What?
Denominator times off because for the j theta it's all plus some bottom and the negative j is plus or minus, but it's
So we can rewrite that, right? Like that, right? So the minus becomes inside. So yes, you got to note that too. So that quantity is opposite. So that would mean that B is a negative value there. And then what do we do with the 3? Yep. So we would do this instead. Let's see, the minus should have a minus. And so then we can move this over and then it's all multiplied by 3. So the 3 stays the same. And we would have 3 here, and then inside would be 2e, and then what is our a in this case? So a is 1. So it'd be minus 1t. And then what is our b? B is going to be a minus 50. And theta so it'd be a plus 1.15 degrees. And then u of t. And so this would be my, so this portion is IC1 of t. Yes.
Are we always doing degrees?
Whatever yours your preference, I prefer degrees. So I'm gonna do most all mine in degrees. Radians doesn't, I don't know, it doesn't look the same to me.
Okay.
I know where 30 degrees is, but I don't know where 5/3 is for me, so. So whichever one, like, looks better in your head, feel free to use whichever component you want, degrees or radians. All right, so now we need to do the same thing for IC2. So IC2 was this component. And so we can kind of rewrite this one as a -6 kind of out in front. And it's going to have the same bottom, right? So it's going to be, again, an A and a B. And so the difference, though, is that you have the e to the minus, or yeah, e to the minus s. Plus 1 minus 50j. So the only difference here is that it is, oh, sorry, minus 6s. So everything is exactly the same except for that e to the minus s. And so looking at the properties here, we notice that if we have this form, which is just e to the minus at times that f of t, it does a frequency shift. So all we have to do is use this property. Wait, sorry, wrong one. This property in. So when it's in the S domain, you have e to the minus ts is going to transfer over as that one. So verify these are the same. So we have exactly what we just did, except for in the S domain, we have the e to the minus ts. So t in this case is a 1. So we have a capital T is equal to 1. And so we can use this property to get IC2, which is just going to be the shift. So minus 6 e to the minus t minus 1 cosine 50t plus 1.15 degrees u of t minus 1. So now we can just add those two together. So we have IC of t total is going to be the solution of IC1 plus the solution of IC2. So 6 All right, there it is. That is our solution. Would have been a pain to do by hand, to do all of the integration and differentiation. The questions? Everybody following the steps I did? Yes.
Can you go through that step and just did for IC2 again, transforming back to the time domain?
Yeah.
Like, I guess looking at going back to like the original IC function, Like, I guess what were you, how did you know? It just felt a little fast to go from -6s e to the -s, like, to basically form that function. I understand that you're seeing some similarities between the IC1 equation and the IC2, knowing that like I see that. Okay.
So IC1, we said was this one. Or before it even was factored was this one. So that's 6s over s squared plus 2s plus 2,500. And so we just noticed that it's the same except for a minus. And we know the minus just comes out in front. So then it's just IC1 times e to the minus s. And then we notice that that t is 1 and we can move it back. Does that make sense?
Yeah, when you put it in that negative IC1 and multiply e to the negative s, that made a lot of sense.
So with that, it's like, okay, I mean, otherwise I could go through the whole thing again and do
Yes.
my A and my B and solve for those. This method, by the way, is called the residue method. Should say that. So if you come to that in math, that's what this is called, is the residue method for partial fraction decomposition.
So. Different methods, I was very confused on that part. Like I have this partial fraction. So does either way work?
How did you learn partial
You
fractions?
take whatever, so 6s over the 2 factors, you just said that with an a over that, plus an a over that, and then you would multiply across and get a times the other 0 plus b times the other 0. You distribute it out, and then solve for it like each s, so that you like solve it different linear system.
Okay, yeah, you can use that same method. It gets a little bit more complicated for some of these that are complex. Did you have a question or comment, Taylor?
Well, I was just curious, is the residue method for partial fractions, is that, well, I guess it looks like- yeah, so is that only applicable when you basically got like some form of a like kind of function, the polynomial in the denominator where it's basically like the product, I'm trying to narrow the math term, but I can see it's s plus 1 plus 50j and s plus 1 minus 50j. You basically kind of have that type of framework, then you can use the quote unquote residue method.
So you can use the residue method for any of them. So that's what is nice about it, because even the polynomials, like he was saying, like I've learned it with the polynomial
That's
and
how I
then
learned it, too.
you match it up. So with the residue, it just makes it easier to find those for any of the forms that we may see. So f of s is usually, for our systems, we'll either have like a distinct real. So I'm going to back up to these. So when you have let me find this one. Okay. So as you know, an equation like this, if you get it to this type of an equation, you're going to have what are called zeros and poles. And any one in the numerator is going to be, when s is 0, that solution is called a 0 location in this S domain. And so that is actually going to correspond to a frequency. So that real imaginary plane that I talked about at the beginning, this will be a point on there that will translate over to a frequency value. And so that is good for us to know, because then we can learn how to graph it, which you're going to learn in 2280. And that corresponds to a frequency, and each of those frequencies changes the operating range of a circuit. And so that's why we want to learn this, is because that will help us learn what's called the bandwidth of a circuit and where that circuit is going to operate as far as the frequency ranges it can operate in. So we have to understand, okay, well, where do you get that from these equations? The top is going to be a 0 and the bottom solution is going to be a pulse. So in this case, the zeros here will be when 10s plus 16 is equal to 0. And so that will be when s is equal to a minus 16 over 10. So that would be called our 0 location. And it will actually translate over to a frequency if this was derived from a circuit. And so these will be in radians per second. So this would be 16 over 10 radians per second. So on this graph, that location doesn't have an imaginary on it. And so it will be just right here, and we do a 0 at minus 1.6. And we do a circle for 0. And then for the bottom, they're called poles. Where are pole locations going to be here?
S equals 0, -2, and -4.
Correct. And so again, no imaginary portion on this, so they're going to be just on the real axis, and then that would be 1 at 0, and for the poles, we do an X. So it would be a pole at 0, a pole at -2, and a pole at -4. And what you're going to learn in 2280 is that at each of these frequency locations, these are actually radians per second as the default unit. And it affects the circuit at each of these locations by altering whether it will go from maybe a flat graph in the magnitude to now it will drop down or it will drop up. And so it shifts that graph. And where it's flat in the graph is where the circuit will operate. So you're going to learn that in 2280, but I just want you to understand, like, this is the motivation of why we want to know this information. So for you guys, what you need to know is just like, okay, I have this in this kind of real and imaginary plane, and I know these locations, poles and zeros. And so from this, we're always going to have, because we have real systems, they're going to be one of these forms. I'll either get a distinct real pole. So in this case, the pole value would be an A. So minus A, but A is what we just want the magnitude value of it. So we say that there's a pole at A and it's real. We have repeated real poles. When we have like S plus A to the N, that means that I have 2 poles at the A location. This one is going to be a distinct complex form, and this one would be a repeated complex. So these are the ones that we're always going to boil down to, is usually one of these 4 forms from our circuit. And so from those, we need to find what is the A values so that we can then transfer them over to the time domain. So these are the main ones you're trying to get to the form of. That makes sense? Okay, so let's look more at that partial fraction expansion. And let's look at something like this, where we need to solve for A, B, and C. So you are welcome to use whichever method if you've already learned this in math, you can use that method. Otherwise, I suggest to use the method that I was suggesting, where for A here, you would multiply the equation by S and then put S equals 0 would be your solution. So it would be 10S plus 16 over S plus 2, S plus 4, and then evaluate it at S equals 0. Yes.
You might just start with these. So how do you, so you take the from the original equation, and you just have the zeros that work in the bottom,
Yeah, you just multiply this by whatever, whichever one. So this one will be S. For B, it's going to be multiplied by S plus 2.
You multiply that by your whatever method that's, right?
Uh-huh.
Oh, this is gonna be x equals 0.
So you plug S equals 0 into each one of those. And then this one, you're going to take S is equal to a minus 2.
So you
So-
solve it like that's 0.
Yep.
Okay, got
All right, so go ahead and work on this and see if you can get this answer. Breakout rooms. All right, I'm putting you guys online in breakout rooms just because it's easier to probably communicate. So if you guys want to take a screenshot of this and then you can share in your breakout rooms or just have it written down. So Alexis, sorry, I. Sure. Whiteboard. There we go. Alexis, can you hear me okay? Can you guys hear me okay? Maybe. Okay, so you had a question about the 6U. Sorry, this whiteboard's kind of yucky. Where was it? It was. Okay, this was at 0. And this one was at 1 second. And so how this was, so you know that U of T is going to look like this at 0. So it's going to change at 0. And then you know that you have a time delay is going to do it at the exact. So if this is at 1, then this would be u of t minus 1. And so this was at, it went up to 6. So in order to get this to go to 6, I would do 6 times these. And then in order to get this graph, I need to take this minus this one. And so this value here is going to subtract off from this value here. And so at the beginning, if I subtract 6u of t, and I subtract off the 6u of t minus 1, then change the color. You know, here in this section, it's just going to be 6u minus 0. But then once it hits 1, it's going to be 6 minus 6. And so that will become then 0 down here. So this would be how you would describe that signal. Does that make sense? Okay, great. All right. I will see you guys in a minute. Keep working on the partial fraction expansion. Minus 20. Minus 4. All right, welcome back. All right, so you should have found for A to be 2, B to be +1, and C to be a -3. From there, you have the form of 2 over S plus 1 over S plus 2 minus 3 over S plus 4. And then using the relationship of the 1 over S plus A, that transforms into e to the minus AT U of t. And so those transform into 2 plus e to the minus 2t plus or minus 3 e to the minus 4t times U of t. Questions? Anybody have any problems with this? Yes. So the numerator just gets multiplied by that, yeah. So that was one of the properties, just a multiplication by a constant. So when you have a multiplication by a constant in that S domain, it just multiplies the time domain result. So this relationship is where that came from. All right. Other questions? Okay, you ready for a little bit harder one? I'm seeing those. Okay, test your knowledge is a great place to get some extra practice on this because they'll pop up some of these to do the partial fraction expansion. Yes.
In this case, if you like, fracking out S plus two and did it like right it 2 times, would A equal B equal C, basically, so like all of your A, B, and C are all equal to each other?
On this next problem, you mean, or? So that leads us to this problem, which is what he's asking. So in this case, when you have multiple poles, you actually have to write this as A over the first one, S plus 2, B over S plus 2 squared, and then C is going to be S plus 2 cubed. This one's a little bit different now that we have this because you can't just say it's S equal to minus 2 and then multiply it because they would be all the same. So for this one is a little bit different. We're going to use the repeated real poles. And so we actually have to take the derivative to find these. So for the first one, you do the S plus 2. And then for the second one, a derivative of that. And then the third one will be a derivative of that one. So that means like the first one for A is going to be 4s squared minus 15s minus 10. And then you're going to multiply that by the S plus 2 cubed. So those cancel, and you're going to evaluate that at S equals minus 2. For the second one, you're going to take the derivative of this. So the derivative of that is going to be you multiply it first. So multiply it first and then take the derivative. Yes.
Why do you have S plus, why do you multiply it by S plus 2 cubed? Or is that from like the theorem?
This is just the theorem of it. And so you have to take the derivative. So we're going to take the derivative in this case with respect to S of the 4s squared minus 15s minus 10. And then C is going to be the derivative of that. So that gives you the second derivative. So this is going to be the result from there and take the derivative of that part. So go ahead and take a minute to work on that and see. Oh, and then you evaluate these also at S equals minus 2. So it is the, it has these, but they cancel out. So you're taking the S plus 2 raised to the cubed. I don't know if that helped. So you are multiplying it first and then taking the derivative of that. All right, I'll put you guys back into the breakout rooms.
I got mine. Why did I write it? Oh, yeah, I should be 36. I just can't really do that.
Sorry, I have these backwards. So this should be, this one is C. This one is B. This one is A. B1 is, wait a minute. Yeah. Yeah. So I had those backwards. So C is the one where you're multiplying it by s+2 cubed. And then it's the derivative of that one for the second one, and then the derivative of that one for the third one. The what? Yeah. So A will be the second derivative. Yes.
Say we have an additional pole, like we have a pole that was like the value as we still have to evaluate it the same way.
So with that one, you would do the s+2 cubed portion this way, and then for the, say it was, there's one in here, let's see. So like an example like this, where you have s+1. So for this one, you would evaluate the A1 just by multiplying it by the s+1 first and evaluate it at s equals -1. So the bottom would still have that s+2 cubed. That makes sense. Oh, sorry, this isn't that one. Where did it? Okay, done. There we go. Pulse. Yeah, here's the example, sorry. So you have x+2 and then s+3 cubed. So you would have a over s+2 plus b1 over s+3, b2 over s+3 squared, and b3 over s+3 cubed. So the first one for A, you would just multiply it by s+2. And then evaluate it at s equals -2. And then for the B1, B2, and B3, you would do it what we're doing now, is you take the derivative of each one. Say that louder. Yep. Yep. Yes.
So let's say you have like. A would be. When I'm, sorry. Okay. So we take it to the fourth, would, if you had one more term, let's say, let's call it B0, right? Would it be 1/3 factorial then? Or how is the factorial? Or only gonna be two, you see what I'm saying?
Yeah. Yeah, so it's always 1/2. So, oh no, I see what you say. Yeah, I think there was, no, that's squared. I'll have to look at that one. I don't remember. I think it does become a factorial, so I think it's 1/3 factorial if I remember right, but I'll have to go look that one up.
And then you just have to write it.
Mhm. Yep. So the example in the book, I suggest, you also go over to see this. The one thing about the one in the book is that you have two components that are multiplied by each other. So you have to use the chain rule of the first times the derivative of the second plus the second times the derivative of the first, but you have a -1 from the bottom portion, so.
Yeah.
647. Yeah, so 647 has these repeated poles. All right, so on this solution, you should have found that C, so for you guys that were online, I had a mistake, so do make sure to correct that. C in this is going to be actually the one that's multiplied by the s+2 cubed, and then A is the second derivative one. And so when you transfer this over as the inverse, you're going to have A is 4, so it's going to be the first one, 4e to the -2t u of t. I'll save the u of t's till the end. And then B is going to be the -31. And then that is the second derivative, or second, it's a squared, so it's t in there, e to the -2t. And then the third is going to be a 30, oh wait, I have 36. How did I get? Oh, 2 over so because of the 2 in the top, you have to divide it by 2. So that will be 18. T squared e to the minus 2t, and then all of that is multiplied by u of t. So the 18 comes from the 2 of this one. And so you have to take 36 divided by 2 to get. So you need it to be of the form. So to get this into that form, C is 2 times 18 to give you 36 over S plus 2 cubed. So when you change it over, the 18 is what comes out. So this is 18 times 2 over S plus 2 cubed. This portion is what the table is. And so you have the 18 is what comes out front. Does that make sense? All right, so Monday, there's going to be assessments. So there'll be a partial fraction expansion to work on. And another assessment. I haven't decided yet what it is. And then there'll be a quiz on Tuesday. Oh, I forgot to do the unit 1 feedback. Yeah, I'll change the due date for that and post a unit 1 feedback. Thank you for reminding me about that. I forgot I posted post 1. All right, any questions online?
No, I think we're good here. It'll just be.
All right, anybody
practice,
have any
practice,
questions
practice.
online before you go?
None from me.
All right, see you guys.
See ya.